Okay, it seems like we are live. This is the first live stream I've ever done, but I thought we'd just go for it. And what I wanted to do is read through the Annotated Transformer article that's available from Harvard University, which is a annotated version of the Transformers is All You Need paper that's quite famous recently. Annotated version of the Transformers is All You Need. Okay, everything seems to be working. Okay, so let's go through this. As you can see, I've already started copying some of the code, just the preamble and the import statements, just to see if this will work on Google Colab. We might encounter some errors as we go. I haven't executed any of the code from this article at all, and if this doesn't work, we might have to switch to maybe just Google Cloud or a local notebook. Although maybe we can even execute this here in the within the browser. Let's see. Let's see if maybe we can. Okay, maybe just to be sure. Yeah, let's see. We'll just try this on the Google Colab, and then if that doesn't work, maybe we can just clone this repository and run this locally. I don't have a GPU on this machine, so I'm not sure if this will run out of the box, but I guess we'll see. Okay, so the import seems to have worked. Just copy this and then copy this. Let's see what this does. Okay, these are just, I guess, empty useless classes and some helper methods. Okay, so I guess this is kind of already pretty good summary of what this architecture does. Like it says here, rather than requiring more compute for tokens that are further apart in the input. The transformer structure using these attention heads, does this in a constant number of operations, but then what you get is sort of just an average from these attention heads rather than relating individual positions. And maybe I need to comment here that I'm not really familiar with with any of the deep learning literature or any of the sort of key papers apart from this one maybe. And so I'm just reading this, trying to better understand how this works. I mean, maybe it's a comment that can be made here is, I mean, this paper is from when it says 2016, I think. '17 maybe. So again, I'm not too familiar with the literature, but other models that sort of came before, models for translating text. This particular paper is about a model that can translate text, but also for generating natural language. Models that came before this architecture, as far as I understand, they use some form of explicitly modeling sequences of tokens. So tokens that have a particular order to them, and that is built into the architecture itself. So, excuse me. So these recurrent neural networks is basically networks that where the same architecture is repeated sequentially, and outputs from one bit of this repeated architecture flow into the next bit, explicitly modeling sort of sequential data processing. And then convolution, again, I'm not super familiar with all of these different approaches, but with convolution, there is an explicit spatial relationship between different tokens that's encoded in how you convolute the, I'm guessing, input in these models. Okay, so I guess this code will kind of codify this encoder decoder structure. So let's look at this, but I guess this should be taking some form of input sequence of numbers which represent input tokens. Do something with that to transform it into a representation, and then from this representation, again, an output sequence is generated. Yeah, okay, and then it does this sequentially when generating the output. Okay, so call it decoder architecture base for this, many other models. So okay. So, I mean, the only thing that has some logic other than just creating structure, as far as I can tell, is basically here, where this is just a linear network layer. I'm also not super familiar with PyTorch notation, but this is just a linear layer, which I'm guessing this is probably input dimension and maybe output dimension. So it takes in the vocabulary size, and then, or maybe this is like layers, let's see, in features, out features here. So it takes in a defined dimension of input nodes, and then outputs vocabulary size output nodes, so that it can predict which, basically this will be, ideally this will be one of the tokens in the vocabulary that's being predicted from this input, and then the softmax just selects one of them and normalizes the output. And this is just yeah, okay, so this is just, it's not even, yeah, so it's basically just a linear layer with softmax. Okay, and this is just basically a stack of n layers. It's just, okay, it's just what it says here. And then I guess when initializing this encoder, the type of layer can be set. Let's just quickly look up what layer norm is. Okay, PyTorch, that's nice. Okay, so I guess this just removes the expectation value, divides by the variance, or square root of the variance. What's gamma? I guess some sort of normalization factor. And then shifts the whole output. I'm guessing there's probably some practical reason for doing this. Normalize the activities of the neurons. Recently introduced technical patronization. Summed input to a neuron over a mini batch of training client. Summed input. Okay, it seems like some sort of optimization that's being done to while training. And so I guess it's normalizing the input to a node. Okay. Well, I guess, but so I mean, maybe setting aside, but we can see that in the forward pass, it just goes through all of the layers and then normalizes at the end. So I'm not really sure. I guess without reading this paper, it's not clear to me what the exact advantages of doing this, but seems like it's some sort of optimization to improve training efficiency. Is that right? Training efficiency. Yeah. This maybe for another time. Okay. Oh, this is by Jeffrey Hinton. Interesting. Oh, and then I think I've seen this name before. No, maybe not. Well, I guess they implement kind of their own class here. Maybe this isn't the PyTorch layer norm then. Let's just check that. It's probably undefined. Yes, okay, so this is this and not the PyTorch one. This is just initialization, and then I guess so the layer norm just does mean standard deviation, and then yeah, I mean it just does what it just said in the just does what it said here. Is that right? Self epsilon, standard epsilon, and then the bias. I guess it doesn't have the there it is. Here's the yeah, so this is the gamma from that equation. This is the epsilon from that equation. And this is the beta from this equation right here. There's some way to do this. Yeah. I mean, I think you've probably seen this, or you've probably understood already, but this is just that equation. And then the mean is here, and then I guess it doesn't take the square root, is that right? Just the mean. Standard deviation. Yeah, I mean this is slightly different, but it's essentially the same as the square root is slightly different, but these parameters are basically the same. And it's doing something at least similar to what it says in the paper that's quoted on the side here. Okay, again, this is just residual connections. Okay, residual connections. I don't know, this seems weird. This should be done here, but residual learning framework, use the training framework. This is all just optimization stuff to train the network. Okay, this is also just optimization, but I mean, I guess it does what it says here. It's, the output of a layer that uses this sub-layer connection is basically, instead of just the output, it adds the input and then applies the layer norm. Not sure why, but I'm guessing, well, it says here. Sorry, I'm eating some roasted cashew nuts here. Well, it says here they have empirical evidence that this is easier to optimize and gains accuracy. So, I mean, without reading this paper now, I guess we just have to take that as it says here. I mean, I don't want to go through this in detail now, but I mean, this is basically what it says here, right? So it sort of bypasses the output, adds it back, and then I guess at some point I'm assuming that they take that layer norm that we saw earlier again. Interesting. Yeah, and then I'm guessing this is kind of the architectures that they compared. I mean, like I've said, I'm not really familiar with the deep learning architecture, but this is something I've heard or read a few times, that a lot of these papers are basically, there's very little understanding as to kind of why a certain architecture works. Maybe, again, this particular paper might have more explanation, but a lot of the papers I've seen and taken a cursory read, they sort of present a certain architecture that has been tried in the paper, and then they give empirical evidence that it improves on some sort of metric compared to other networks, or other architectures, but there isn't really a theoretical understanding as to why a certain architecture may or may not work better or worse than another one. I'm assuming that in this case, because it's a very specific sort of tweak, that they have some understanding or intuition for why this would work. But yeah, it seems pretty typical of the literature that that is more of sort of a phenomenological approach rather than something that has a deep theoretical understanding behind it. Okay. Well, here it says the model is 512. It doesn't say that in the code here yet, but I'm guessing maybe that will come later. But here's another thing from Torch, from PyTorch, just a dropout structure to improve, again, learning efficiency. This is something that I've, maybe let's just take a look at the documentation really quick. Dropout, maybe this will bring up Torch. Yeah, it does. Yeah, so this does what it says here. During training, randomly zeroes some of the elements of the input tensor with probability p using samples from a Bernoulli distribution. Each channel will be zeroed out independently on every forward call. Yeah, so basically, rather than taking the input, the full input, and computing the forward pass from that, it randomly clamps some of the values to 0, which means that that bit of the input no longer has any influence on what the output can be. And that has proven to, well, it says here, this has proven to be an effective technique for regularization and preventing the co-adaptation of neurons as described in this paper. Okay, that's, I guess, not so easy to understand, but basically it helps prevent overfitting. So you're showing this network examples, and you're doing this all the time. So with many examples, maybe repeating the examples, so it will try to kind of overfit on these examples, and by rather than showing it the whole example, taking away bits and pieces, you make it adapt to sort of be able to predict to, let's say, defective input, right? Input that has values missing, that has values set to 0. And those are picked randomly, so it cannot fit on the information that's remaining, but has to find parameter values that work, that give a good prediction when random pieces of the input are missing. Again, this is just to replicate. I'm assuming this is not necessary. This isn't necessary to make this whole architecture work. This is just to again prevent overfitting and to make the training more efficient, I think. But again, this is just replicating the paper as it is written. So I'm assuming that's why also this code has this bit. Okay, so now we're coming to the attention bit. Encoder is made up of self attention and feed forward. Follow figure 1 left for the connections. Okay, so again, this doesn't have much code here yet, but this should be kind of this bit. Okay, so, well, I guess we clone this twice, sublayer connection twice, sublayer connection we just discussed. I guess that's this bit. These are just feed forwards then, I guess. And then I mean, I guess this is this bit, right? So first we do sublayer, the sublayer connection, the first one. We take the first one. So here we have two clones, right? And then when we forward, we out of the two clones we take the first one, and the sublayer connection that we just discussed basically ensures this bit here, right? So it input comes in, it's kind of sidetracked here. I think there's a technical term that they use to say that. What's that called? I don't know, that's not the right paper. How did they call this? Shortcut, yeah, I think. So they add this sort of shortcut connection here, and then that's added to the output of this sublayer and normalized with the layer norm, right? So that's basically what this sublayer function here does. And we have two clones of this. Take the first one, and then this takes sublayer takes okay, so this is from an end module, so I'm guessing if you call that calls just the forward function. Yeah, so and then forward. Yeah, you should call them module instance. Okay, yeah, sorry, I'm not so familiar with the PyTorch code, but in PyTorch you just subclass the nn.module class, and then when you call the instance of that object, it calls the forward function, which in sort of the neural network world, it just means, okay, takes input, computes something, and forwards that to the next stage. And again, so we've seen, okay, we've seen first sublayer connection, it's this bit, and then the function it computes is this multi-head attention, and that's basically here. So it calls forward with input x, and then the sublayer function, which is the self-attention function that's defined here. Okay, so we still need that we need to define that in the next step. And then it gives the, so here, 1, 2, 3 is also what you see here. I think these have different, these I think we'll see are called like key, value, and what's that called in the original paper? Key, value, and something else. Query, yeah. So there's 3 copies of the input. You can also see that here self-attention will have 1, 2, 3, and just this mask is just depending on whether you're in the encoder or decoder, we will mask some of the bits of the input, but basically there's 3 copies of the input, query, key, value, and these serve different functions. We'll see that later, I think. And that's also why in this picture that's taken straight from the original paper, I think you see that these 3 lines here. Okay, so we've got that. So we did the first bit, and then we do, going back to the picture, and then we do another sublayer, now the second copy that we've done here, and then within that is just feed forward, basically. So I think I've seen the video by Andrew Carpathy. If you haven't seen it, the Nano GPT video on YouTube. This is pretty great, which basically does something similar as in this paper. He builds basically this architecture from scratch in Python. And I think basically I remember him saying something like, okay, so the network in this first bit, it can do attention, so it can, input comes in, it can look back, or I think in the case of the encoder, also look forward. It can look at the whole sequence of tokens, decide sort of which bit is important, weigh those, add it, move forward, and then you just give it one more layer of, you can do linear feed forward with weights. You can do some computation before taking the final log norm, right? So instead of just going, okay, attention is all you can do, you give it one more layer to do one step of computation with the output that you get from the attention mechanism, and only then do you get to the final log norm that and softmax. Sorry, that's the final softmax, and deciding what the output is, basically. Okay, we've got this bit, encoder layer, got it, and then decoder. Okay. Oh, well, I guess maybe we need to execute the one bit that I didn't execute here in the beginning. So that's like downloading I guess the data that they'll use for testing this. Stop. Okay, stop. Yep. Okay, let's do this again. Yep. Okay. What is this? Okay, yeah. Well, I guess it's trying to. The package space it load. Okay, sure. It's still running. Yeah. Got all the packages. Okay, sure. Okay. Okay, where was that? Where were we? So we've got the encoder. Yeah, decoder. Let's keep that here. Is there some way to hide this? Yeah, maybe. don't know. So, decoder. Memory, source mask, target mask. I mean, I think this looks basically identical to the encoder. Let's see. Encoder is self-attention and feed forward. Sorry, that's not what I meant. This bit, right? Pass the input and masks through each layer in turn. And there's some memory, source, and target mask. So this is slightly different. Can we see that here? I mean, this bit is identical. This bit is also the same, except different inputs. I'm not sure what the memory bit is. Maybe we'll see that. But otherwise, the structure is the same as the encoder. In addition to 2 sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention over the output of the encoder stack. Similar to the encoder, we employ residual connections around each of the sublayers. Well, I guess residual connections is the term they use rather than shortcut. Followed by layer normalization. So that basically they're just saying we're doing the same thing that we've done before, which is this, right? Okay, inputs go in here. There's this residual connection here that sort of bypasses this multi-head attention bit. And then we do we take the input added and take the layer norm, which is this bit. And then I guess this is now going to explain this whole thing here. If you look at the forward function, the last bit is this feed forward bit, which is gone backwards just to, because I think this will be a little bit easier to understand. Yeah, okay, so again, we have, instead of these 2 sublayer structure components, we have 3, 1, 2, 3. The last one is the feed forward. The second one is just self-attention, but is attention, but with getting 1 bit of input from what comes out here, and then getting the 2 bits of input from what I assume later will be the output of the encoder bit. Okay, so this is also, I think, a difference to Carpathy's video. In the video, these 2 bits, these 2 sort of left-hand and right-hand sides of this diagram exist because this is a translation architecture that can translate from one language into the other. So this bit takes one language and then embeds it, also encodes it, does something with it to come up with some sort of representation of what this language, what this sentence may be trying to say, and then gives that representation to this right-hand side of this architecture that when training sees the translated output and then here correlates, okay, so when I'm trying to say this output bit in the original language, is this right? Maybe I've got it the wrong way around. No, but I think it should be okay. I think conceptually this should be true. Anyway, so I'm trying to say this sentence in a language, and then in this other language, even though the model can see sort of the original tokens, in this other language, this is represented in a certain way. So if I see this sequence of numbers that's supposed to mean something in this first language, then in the second language that I'm trying to output in, this is what it should look like, basically. Maybe I've got the inputs and outputs the other way around, but anyway, this is kind of I think these are the roles for the left hand and the right hand bits. They see different languages, and then one is trying to compute some sort of representation of what is being said, and the other bit is learning how to take that representation and then output a meaningful sentence in the target language. And then in Carpathy's video, he's just building a language generator, not like a Markov model, but something that takes input and then completes that input in the same language. And so he doesn't have these two sides. He just has I think he just has the decoder side. Okay. So I guess kind of the bits that we're missing is, if we just quickly look at this diagram again, we understand what this layer, how they call it, sub-layer connection is. So basically you have these residual connections that take the input around what's happening here. You add and you use this layer norm that's described in this one paper, but again, it's just some sort of normalization and weighting function that just normalizes the output. So basically, rather than just going through this attention bit and doing whatever the attention is doing, rather than doing that, take some of the input, bring it around, do the layer norm thing, add one more feed forward layer here, again with this residual connection structure. And then same thing on the other side here. It's just attention with different inputs, feed forward, and then these residual connections. And then at the end, okay, there's one more linear layer here, softmax, okay, sure. I think, at least to me, that bit, all of these bits seem pretty straightforward. We just now need to understand, okay, how do these multi-head attention bits work? That's one bit. And then I think there's this may also just be an optimization thing, I'm not sure, but there's some bit here where instead of just doing the input embedding and using that as input, they add some sort of position information back to the input. So this sort of yin and yang kind of symbol bit here, and then the multi-head attention bits, those we still need to understand, but the rest I think we've got. Okay, decoder layer, yeah, we have that. So we also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent position. Yeah, this is just in the, okay. This masking combined with the fact that the output embeddings are offset by one position ensures that the predictions for position I can depend only on the known outputs at position less than I. So this is for the output language bit, right? When translating, the network is allowed to look at the whole sentence that it's translating, but when generating the output, it's only allowed to see what it has output so far, right? So if you're translating a sentence from one language to the other, like the order of words may be different in these two languages. So in order to translate, you need to see the whole sentence before you can translate it. I think that makes sense even without the word order a bit. But then when you're writing language, whatever the next bit is, whether that makes sense or not depends on the existing bits so far and can't really depend on what's coming in the future. So with this masking, you prevent the attention from looking at certain positions in the token sequence, looking at positions that are in the future, not in the future, but that are past the token that you're currently looking at. So this is just, making the network do what we would like. Subsequent mask, that's, I guess, is why they call it subsequent. So it doesn't mask some sort of complicated structure in the input sequence. It just, there's a token that we're looking at now, and it masks subsequent tokens. And so I guess the way that they do this is, this is much more, return subsequent mask is equal to 0. I guess I'm assuming trio is probably some sort of triangular shape, upper triangular matrix. Yeah, so upper triangular part of matrix. So everything is set to 0. Yeah, so I'm assuming the input that's going in is at that point already centered. So the current token is this sort of the central token, and then in the tensor that we're looking at, the upper bit is triangular upper bit is the tokens that come past beyond that, and the lower triangular bit is these other tokens that have come before that. Have come before that token. And then attention shape. What's attention shape 1? Okay, this is just to determine the size of the tensor. Yeah, and then this just returns like a true false mask that we can use below the attention mask. Have example mask. What is this? Okay, this is just an example. Let's see if this works. This is just, I think, an example that the author of this particular article added to make this more visual, but oops, this we don't need to execute again. Well, sorry for that. See if this works. This, I think, will be the first bit of code that actually does something other than just defining stuff and importing stuff from PyTorch. Yeah. I mean, again, this is just a picture of... why does it do that here? Why do they do that? It's just a picture of a upper triangular matrix mask. Yeah, I mean, I'm not sure this was necessary, but I mean, maybe just to play around with this, if we make this, let's say 15, or let's just make this 6, like a smaller matrix, then you can actually more easily see, I guess, the individual cells here. So the diagonal is allowed, and then anything above the diagonal is in this case here set to to, well, it shows as 1, but the okay, no, autocomplete. Example mask. Okay, so show example. Example mask. What? Example mask return. Okay, interactive. I see. What I wanted is to show this bit. What for? Okay, sorry. Let's skip this. But again, so he in his picture, what they're going to do with this mask is apply it to some other matrix, and then the values here that are yellow will still be preserved from the original matrix, and just the darker bits here will just all be set to 0. I think this is, I don't know why I'm going into details here. I think this should be clear. Okay, finally, so now attention. An attention function can be described as mapping a query. Oh wait, how much is this? I think we'll have to continue this tomorrow, because it's already 20 past 11 here, and we're only like maybe 25% through. But let's read this attention bit, because that's really the juice of the whole thing. And then we can come back to this bit, repeat it, and then move on tomorrow, because I think this will be the most interesting bit. So, an attention function can be described as mapping a query in a set of key value pairs to an output. Query, key value. Okay, so there's some data structure, key value pairs that we have, and then there's some sort of query that's being executed against that, and we get an output, where the query, keys, values, and outputs are all vectors. Okay, so these are just, okay, so it's a list of, query is a list of numbers, keys, values are a list of numbers, outputs is a list of numbers. I don't know why they say vectors and not arrays. And like, why do they, so it's a bit of a tangent, but why do they call these things tensors and not just like matrices? Maybe this is just my background, but vectors and tensors, to me that implies that there's some sort of, that these things have certain behavior under transformations. Or that there's some sort of operation that you can do with them that's not adding or multiplying, that where they have a sort of a defined behavior that just a list of numbers would not have. And I think, to me, especially because this is computer science, calling these arrays and matrices, it seems more natural, but maybe there's something behind it that I don't know, or maybe this is just the terminology that has that's being used, but would be interesting to know if there's something more behind the naming of these, like why people call these things vectors, and the multidimensional matrices that are being used, why they call them tensors rather than just matrices and arrays, really. Well, I guess it's, yeah, no, I mean, I guess maybe it's because maybe because you can, because they take matrix times this vector sometimes, and then I guess nobody uses the term matrix times array, so that really doesn't make sense. So maybe it's from that, but anyway. So the output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So the key is like, here's how important I think these values are. And then the query is, I want to look at this specific set of values. And so if I just want to look at the first one and like the last one of the values, but somehow whatever keys is thinks that only the first one is important and the last one really isn't, then you'll get basically the first value. And so keys can be like a distribution of importance over the values. And then query is, okay, I want to look at these bits out of the values, but please also tell me how important you think these are. Queries and keys of dimension dk and values of dimension dv. Weighted sum of the values, where the weight assigned to each value is computed. Okay, so maybe, so the keys are not like one-to-one with the values. Keys more like each value has a key and then each query. So this can be like, this is not like a scalar, but it's more like a multidimensional key for each value, and then the query. So it's like for each value you've got this complex list of numbers key, and then the query can be quite complex, and then when it fits you get that value. Man, I'm really enjoying reading this. This is quite fun, actually. Okay, so, and then the particular version of attention is called scaled dot product attention. The input consists of queries and keys of dimension dk. Yeah, and then values of dimension dv. Okay, so values can also be multidimensional, I guess. And we compute the dot product of the query with all keys, makes sense, and divide that by the square root of the dimension and apply softmax function to obtain the weight on the values. So we do queries and keys dot product scale, that's probably this bit, mask, optional, doesn't say that here, so forget about it, and then softmax. So basically we say why does it want me to look at torch, but why not? I mean, we've been looking at the torch documentation. Okay, so we have one query, we do cross product, sorry, dot product with all of the keys. We get, is that right? We scale, we do softmax. So basically we essentially get with softmax the this will give you a vector that tells you, okay, out of all of the keys, this one matched most with the query, had the most overlap with the query. I don't know if you have like a linear algebra picture in your head, but the dot product will be largest for when the keys in a query align most in. I mean, I can only show this in three-dimensional space, but in the multi-dimensional space, that these are in whenever these two vectors, so the vectors defined by the query and the keys, when these align most, dot product will be the highest, and then the softmax basically just is an example here, maybe normalizes this, but also accentuates the highest values. Maybe let's go to the Wikipedia page again just to converts a vector k of real numbers into probability distribution k. I mean, normalization, sure, but isn't there some sort of picture here? To show the effect of the yeah, maybe this. Show the effect of the softmax. Or this one is also fine. So there's some sort of distribution of output values here. Some are kind of small and negative, some are medium size positive, some are big and positive, and then softmax converts that into a distribution of values that sums to 1, and also keeps the order of these items, of course. So the smallest items are still the smallest over here, largest are still largest over here, but also large values tend to be like really close to 1, and the smallest values tend to be really close to 0. So it kind of stretches that a little bit. Okay, in practice we compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of outputs as softmax. Okay, so matrix Q times K. So it's basically the same as what it says here, but instead of doing matrix times query vector, you can just put this all in one giant matrix Q and K. And then why do they, I guess then this, yeah, so the softmax here basically creates like an output that is like a mask that selects certain dimensions, that basically what we just saw here. So you do dot product of query and the query and keys. With softmax you're left with sort of numbers close to 1 in the dimension where the query matches the key, and then that's multiplied with the values, and so you're basically left with the only the values that are relevant, that are whether the entry is 1 in this softmax output. Okay, but then it's not clear to me really how where is the nice picture? I guess these are saved. Save a copy and drive. Can we save this? I think this should be saved with my account. it's not really clear to me what is the dimension that we pick for these, because there must be some useful relationship between the size of the input, which I guess, again, I'm sure this will be explained later, but that's something that must be something like the window that you're looking at with the tokens. There must be some relationship between that and kind of the size of these attention heads, and then that must be something like that's where like the size of the keys and values and the queries must come from. So like how do these, yeah, I guess the question is how then does the input transform into keys, values, query, and which of these are basically parameters that are being learned. I'm guessing the queries and like the keys are probably being learned and the values will be related to the output, but yeah, how does that relate is not clear to me at this point. But maybe just before we take a break until tomorrow, let's just quickly look at the code for this attention here, query key value. So queries, so it basically, I mean, this just does what it says in this equation. And then it says mask is optional here, so if the mask is given, then it masks. If not, doesn't, then does the softmax. And then I guess does drop out if you want. It doesn't really say that here in the diagram, but the code does have another dropout bit. Okay, so I'm getting a bit tired, so I'll stop here. But I think we just sort of, we're stopping slightly short of the meaty bit of this article, because I think if we read through this and then understand this bit, then basically the question I just posed will be answered. And then here where it says position-wise feed-forward network, no, not sure. Anyway, so this is already the next bit. Position encoding, this bit will explain this other question I had about how they add this positional information for the token. But yeah, but it seems like the attention bit is just these few more paragraphs. So I think starting there and reading that should answer those questions. And so I think we'll start again basically here and then understand that bit. All right. Thanks so much. That was fun. And then we'll continue tomorrow.